So this is like part 2 of the talk I gave here like 4 years ago, 4.5. At that time, we were trying to identify some of the characteristics of social networks, and since then, we've been leveraging some of these properties that we found were common. John mentioned, he found that informational networks, like social networks, authorship graphs, pretty much the kind of networks that naturally arise in social interactions on the web, as opposed to networks like the power grid or the telecommunication network at the physical layer, or the road networks. They have some specific features, and we've been able to use these features for computation for big data quite effectively. I'll show you some examples of that at the end of the talk. So let me just give you a quick overview of what we want to achieve. Let me put my timer here. What I'm doing. Okay, so I'll talk a little bit about the key center clustering. Then I'll introduce the hyperbolic constant of graphs and the fact that they happen to be small. Then we go back to some old work from 40 years ago on key center computation on trees. There is a reason why we want to do that, because it turns out that we can inherit much of the machinery that we developed, and they were very nice and simple and elegant for some of the computations on graphs with small hyperbolic constants. So I'll talk about that. Then I'll compare and contrast with what exists today in terms of alternative algorithms. Then I'll tell you a little bit about the results that we've derived as an approximation. That's linear time. So it lends itself very well to very large instances of graphs. In these social network type of graphs, you can easily scale to hundreds of millions or billions of nodes. So algorithms have to be able to scale, and pretty much linear is all you can afford to do. Even simple quadratic schemes fail to work. So that's the good news. And then I'll show you a few examples of the applications of this methodology. All right, so what is key center clustering? Is the graph equivalent of k-means, which you could argue is the most popular clustering algorithm. What is k-means? You have data. In the case of the data in Euclidean space, we're looking for p-points such that the maximum distance of any point to its nearest center is minimum, as small as possible. There's a natural way of grouping data sets. If data come with a natural topology, like in Euclidean space, whatever dimension, then we usually refer to it as k-means. If data come naturally in a graph structure, then you get the so-called p-center. Okay, so that's terminology. And the ones that come in graph structure are harder because they don't have this natural embedding into an existing space that tells us about the affinity or closeness. Okay, it's used in, k-means is used in tons of applications. Just about every clustering algorithm at some point uses k-means. Any kind of spectral clustering, you get a couple of eigenvectors and then you use k-means in order to say where the clusters are. An example is OkCupid, if you know what that is. It's a matching website, and the underlying algorithm uses k-means. just a little factoid that came in. It was actually developed at the labs in 1957 by Stuart Lloyd. He was working on what was then very hot topic, pulse code modulation, and he was trying to do different sampling of the analog signal, and he ran into this. For some unknown reason, he never published it until 1982, by which time a lot of people had written about K-means clustering, and his paper was no longer novel. So one lesson that we learned from Stuart Lloyd is, if you have a good idea, publish it before somebody else. All right, so let's move on to prior work. So, assuming that you're convinced this is an important problem, which it is, net decenter clustering is actually a hard problem to solve in general. Roughly n to the power p combination, so if n is like 10,000 and p is 10, you're not going to get anywhere. So obviously people have looked at it. There is a 2-opt algorithm due to at least one or two papers, Ravi, Rosenkrantz, and Kumar Tai, and also Dyer and Reed. These are very well-known papers that 2-opt, and it has a fairly simple heuristic. We want to do better than 2-opt. R can be large and twice the radius. So I'll tell you the terminology, but remember we want to minimize the radius of these blocks. So we want to, having an approximation that gives us 2R is probably not good enough. There is an approximation that uses the hyperbolic constant was published in the late 2000s. These are computational geometers, mostly in France for some reason. We've been looking at this for some time, and it's a very nice result. Unfortunately, it has a very good approximation because it has an error, additive error of delta, but it's n cubed complexity, which means that you can't even apply it to more than a few thousand numbers. So that's where we started from. We wondered if we could improve this complexity time by giving up a little freedom in terms of the level of approximation, and that's really the core of the work. Okay, so let me give you some preliminaries. I was talking to some of the students yesterday, and it occurred to me that I should not assume some basic definitions. So here we go. Something is a metric space if it has some basic properties in terms of distance. So assume a space of anything, and there's a metric that's defined, meaning there's a notion of distance, and for every pair of nodes you have a distance that's non-negative. It's symmetric. The distance between the node itself is 0, and you have the triangle inequality. Okay. So the metric space is geodesic, or think about it as every pair of nodes has the shortest path between them if there exists a path with minimal length. So in case you think that every space should be geodesic, here's just an example to dispel that illusion. So here's a box, and it's a metric space, obviously. And the distance between x and y, as I've shown them, is the difference between the x coordinates. However, you can turn this into a non-geodesic metric space by simply removing the origin. So what happens is x and y don't have a shortest path. They have a distance, and now we've messed up the space. So it's not guaranteed that every metric space is geodesic. However, we're not going to have to worry too much about this because we're going to deal with mostly discrete structures. And in this case, we look at a graph, either the vertices of the graph or the nodes in the metric space or sometimes we may include all the points on the edges also. So a metric graph. So our focus is on graphs, but occasionally I may slip into the metric space language. Just think about it as the graph. Question. Okay, so the oldest paper I can find that refers to this property that ultimately we refer to the hyperbolic constant of a graph is due to Newman. He worked in Scotland in the 70s, and he was doing something about psychology. He was trying to work on some problems on artificial intelligence, as it turns out. So he was trying to map this similarity or similarity to some metric structure. And he noticed that this property of trees. So if you have a metric space that is derived from a tree as in a tree graph, not just the one that is outside in the field, then what you notice is this idea of taking any 4 points and looking at the sum, at the distances, the 6 distances between them, adding up the distances in opposite pairs. So we have the red opposite pair, we have the green opposite pair, and then we have the purple opposite pair. We add these distances, and then we order them from the largest, medium, and small. So you can do that in any graph, easy. And then you can look at the difference between the largest and the middle one. So what Newman noticed is that this is a way to characterize metric graphs, in that in metric graphs, the distance between the largest and the next largest is always 0. And why is that? You can convince yourself that if you take any 4 points in a tree graph, then the configuration of joining them is either 2 Y shapes that are joined up with a stem, or the stem has length 0. There is no other way to do this. If the stem has length 0, then the sums of opposite pairs are all equal. The distance between AD and BC is the same as AD and BC, the same as AC and B. Because these are just the 4 piece segments added in different ways. However, in the more general case that I've shown here, the largest and the second largest incur the stem, this middle section, twice. And the smallest one just doesn't have it. AD and BC don't have this. So that's why he divided this by 2, because it's that common segment you divide. It appears twice. So this L minus M is a measure that reflects what would be in the middle. So if we do this for any graph, we obtain a constant, which is the largest such deviation from a tree metric, if you like. And Newman argued that if this delta that you compute, we call it the 4-point delta, delta sub 4, if this is small, then your space in some sense is similar. The metric structure is derived from the metric structure of a tree, but it's very close to it. Okay. So that's one key observation. I think that's the oldest one that I am aware of. And later on, other people working on geometric group theory came across the same idea, but they defined delta in a slightly different way, which is more powerful and more useful. And that's the definition that we would use. And in this case, the idea is to look at what is the neighborhood, what is, consider a number delta, and consider a delta neighborhood of each side. And look at the smallest delta so that each side is in the delta neighborhood of the other 2 sides. Okay? So for any triplet of points, such a delta defines a way to see how each side is the union of the other two, or more technically, this is related to the radius of the inscribed circle. So in some sense, the radius of the inscribed circle is really small, no matter how far x, y, and z are from each other. Then the space is hyperbolic. So this is important. I'm going to spend a little time here because we're going to need these terminology notation that we developed here. So you can think of your triangle, since it's a metric space, you can take any triplet of distances from x, y, and z and redraw that in the Euclidean plane. Okay, and in the Euclidean plane, then you can draw the inscribed circle for real, like you did in middle school or high school. And then you get these distances, the distance from z to mx and from z to my, they are equal, and the distance from y to mx and z are equal, etc. So we call these distances internal distances, and the notation is alpha sub x means that it's one of its ends is x. Alpha sub y is this y to z, etc. Okay. So this is a useful notation that I'm going to use, so that's why I'm emphasizing. Points mx, my, and mz are called internal points, and these distances are called internal distances. So you can actually define an isometry between your triangle and this tripod.
But the distance upstairs is different, and downstairs you have Euclidean, correct?
So downstairs is not Euclidean either, it's just the schematic.
Oh, the schematic.
Yeah. In the Euclidean plane, you don't get this picture. You get these two sides lying on a straight line, and these two on a straight line, and the other two on a straight line. And where the inscribed circle touches that Euclidean triangle, you get exactly these distances at the tangent. Okay? So this is the construction. So in this isometry, every pair of points in these lines that I've indicated get mapped to the same point. So the inverse, or the fibers of these, as they're called, are a pair of points. And what these...
The definition of an inscribed circle is well defined no matter what the space is.
No, but we define it by taking the triangular sides and putting them in the Euclidean plane. Okay. Because you have the triangle inequality, you can draw it in the Euclidean plane.
Right.
And once you draw it, you can put the circle, and then you get these distances. But these distances you can compute without doing any of this stuff. The distances, again, I don't know how much geometry you did, but if you take the perimeter of the triangle, divide it into two, that has to be bigger than any of the sides. That's by the triangle inequality. So that difference are these internal distances. So pi, which is half the perimeter, minus yx is distance alpha sub z. Okay. This is actually how you would construct. So again, the whole idea is that triangles become thin because all triangles, regardless of the distance between x, y, and z, they have this, the distance between the internal points is bounded by delta, means that as x, y, and z are going further from each other, the sides of the triangle have to bend inwards. Okay? All right, so this definition is due to Rips. However, Rips never seems to have written anything down about this. So everybody cites him. Everybody refers to his name, but there's no paper to cite. There is a paper with a similar content, a little different, by Roma from '87. Okay, so this is important. And then a key observation, which seems to be missed by half the people who work in this area, is that delta 4 that we defined before, Newman's notion of the hyperbolic constant of the graph is actually less than delta that we have defined. And that is a little bit more work, but it's just pure middle school geometry. Okay? That's the fun part of most of this. Most of this doesn't require more geometry than what we learned in high school, but in a very unusual way. Okay? So this is important because we're going to use it. So in fact, we define a metric space to be delta hyperbolic if all triangle internal distances are bounded by delta. So that's our definition. Okay? And then if we use this definition, then we can be sure that delta that is defined by Buhlmann is no more than what we use. Okay? Sorry about the extra time on this, but you're going to use this. So a useful property, again, high school or middle school geometry, is that for any triangle without loss of generality, assume xy is bigger than zx, which is bigger than zy. And the fact that these internal distances are computed by subtracting these from the half the perimeter, you can see that alpha z is less than alpha y is less than alpha x. So there's an intuitive way to remember this, is that if a vertex looks at the largest side, its internal distance is the smallest. So in this case, z is looking at the largest side of the triangle, yx, so this tangent distance alpha z is the smallest. Okay. Why do we need any of this? Because we are going to use these distances to estimate shortest path. Right? If I want to go from z to somewhere else, I'll show you in a minute. Actually, okay, let's just do a 90-degree turn. So around 2009, 2010, I started a little program to measure data for a whole bunch of social networks. There are tons of them available publicly. Stanford has a ton of them in the SNAP directory. So we looked at these range from a few thousand to 100 to 300 million was the largest we looked at. And then we looked at the diameter, average shortest path, the maximum delta that we could compute by all sorts of sampling techniques, and the average delta. And you can see that maximum delta in all these networks, and these are several dozen. By now we have looked at over 100 of these. You can imagine computation with some work to compute delta, because to exhaustively search for delta, you're talking about NQ computation. And if you have 200 million points, that takes some time. Of course, we're not going to do all of them, but you have to do careful sampling. But the point is that deltas are small. In contrast, in the last row I've included some information that 3 road networks, California, Texas, and Pennsylvania, from the SNAP library. And these are a few million nodes, and you can see that delta is big, 400. Right? In the other social networks, even with the ones with 200 million edges, this is a call graph, 1 month's worth of conversations in some country. The delta is smaller than 6. But we're not sure how to actually identify a closer range, but even 6 is less than roughly a fifth of the diameter. So anyway, the point is deltas are small. Okay, not in all road networks again. In some sense, California and Texas and Pennsylvania do map to a Euclidean space, which is not hyperbolic. Triangles in the standard space get larger, the radius of the inscribed circle gets larger, and there's no bound. So that's why. Okay, so we have this result which says deltas in some of these networks that we'd like to do computations on are small, and we want to take it from here. Okay, so just a couple of definitions, formal definition. So we say C is an R cover for a set if every point in that set is within distance R of that set C. and we say strict packing is just a bunch of points so that the distance between any pair of nodes is strictly bigger than 2 times r. Right? So these are disks that don't touch each other. Right? So immediately by the pigeonhole principle, you know that the best packing that you can come up with has no more elements than the cover. Because if you had more of them, 2 of them will fall in the same disk cover, and by the triangle inequality, the distance between them is less than or equal to 2r. R is a number, fixed number that you're playing with, and that violates the definition of packing. So every time you can find the packing and the covering that are equal, you're close to optimum in some sense. Right? The packing is always lagging behind. Strict packing. Okay, so let's look at how one solves the p-center problem in a tree. Oh, I didn't say, but it should be clear that in a tree delta is 0. All triangles are 0 thick because there is no thickness to them. And remember, Buhlmann also told us that trees have 0 delta. Okay, so this is actually a construction due to Shire. He worked at the National Institute of Standards, not far away from here. A very well written paper from 1977. I recommend reading it. So how does he do it? First, he finds a pair of points that are diagonally formed, x and y. This is an important step. But this can be done in order n in a tree. And an observation here, if you're not dealing with a tree, this is order n squared. So finding diagonal pairs is expensive. In general graphs, it's cheap in trees. So that should give us a hint as why we want to use the property of a tree, because this is an important computation. So what Shear tells us to do is you find the diagonal pair, x and y, diametrical, sorry, not that. And then you set a distance rho, which is you want to cover this tree with disks of minimal number of disks of radius rho. So you do an offset of length rho from one end of the diametrical pair, and you call that center 1. You put it in the bin for centers. Then you draw a disk of radius r. I've drawn it in the Euclidean plane, but the disk in the tree is a little different. And then he observed, and this is the crux of the matter, that this disk of radius rho actually includes the disk of radius 2 rho centered at x. So this little disk actually contains a bigger disk. But it contains it because the bigger disk starts from the edge of the graph. It has no room to go to the left of it. And to the right of it, every point that's 2 rho away, it's still a distance rho from the center. So that's really the beauty of this construction. Which means that a point that's outside this has to be strictly more than 2 rho away from x. So that gives you a packing now. Because I put C in the set of covers, and I put X in the center of, in this set of packings. And now whatever is left is going to give me another point that's a packing. So every time I'm able to find the center and set, I'm able to find the point that adds to the packing. So hand in hand, I'm increasing the covers and packs, so that you see how it, you can show the optimality. So you basically remove this disk and then you iterate, which means next time you find another pair of nodes that are diametrically far, and then you do an inset. If you're trying to find the p-center, you have to do a binary search. You create a table now which says for R1, here is the number of centers, for R2 is the number of centers, and then you do a binary search if you want to solve the opposite problem, which is how many, what's the radius of the disk, minimal disk that I can cover the graph.
Excuse me. Yeah, I think you repeat this idea again.
The idea? So you find the diagonal pair, xy, diametrical.
Diametrical.
And then the rho is given. So you go into on the geodesic, on the shortest path, you go a distance rho. That gives you the location of the center of the disk. So you draw a disk with radius rho, and then you repeat. That's all. The reason why this works is that we are doing a primal dual construction. You're not only constructing the disks, you're also constructing the packings, strict packings. Because whatever is left outside this disk has to be strictly more than 2 rho away from X. That's an exercise you can do after the class. But I'll show you a proof anyway. Okay, so that's this, and I have now explained this.
The most computationally intensive part of this algorithm is the diametrical.
Exactly. That's the most expensive.
Everything else is cheap.
Right. So that was our starting point. All right, so I've explained this. So basically, because the packing and the covering are constructed hand in hand, you have this equality, and the maximum packing is never more than the minimum cover, so therefore that gives you the optimality. Okay, so this is a key observation that reduces order n, anything that had happened before. So now we are not working on trees anymore. We are think about an arbitrary graph. And here we define the notion of a locally diametrical pair. A locally diametrical pair are a pair of points such that each one is maximally far from the other. This doesn't guarantee you that you actually have the diameter of the graph, and here is an example. In this graph, x is maximally away from y, 4 hops, and y is maximally away from x. However, the distance between x and y is not the diameter of the graph, which is given by this vertical path. Okay, that's distance c. But the point, the key observation, is that finding diametrical pairs in any graph is n diameter of the graph. Why? Because I start with an arbitrary point x, wherever, random. Then I go as far away from it as I can. So that gives me something that's extremal in some sense. Then from that point I go as far away as I can. Each one as far away as is an order n computation. It's a breadth first search computation, where you grow a ball of radius 1, 2, 3, 4, etc. until there is no more points left. Okay. So finding, you go as far away as order n. Every time I say that, I add an order n. But how many times can I continue this? That if it stops, if after I find x, the furthest point from x is the same distance as y, I'm done. I found the locally diametrical pair. But if it is more, then I can go up by 1. How many times can I go up strictly by 1? Diameter of the graph. So there's no way I need more than n times diameter. And remember, in our social graphs, this is a well-known fact, diameters are remarkably small. This is a small word property or whatever. So you have, Facebook has over 1 billion nodes, and I think it was 2 years ago they published the average distance between every pair is now less than 4. And the max, it's very small. Diameter is remarkably small. And this is actually true. Co-authorship graphs, any one of these social, this has a property, and people have talked about endlessly why that happens. 6 degrees of the separation, penetration.
Has anybody computed the diameter from Trump?
From Trump? I don't think that would be small. Several friends probably not. So this is going to be a very useful observation because the previous work that was done used diametrical pairs. Shire started with diametrical pairs and people have stuck to it. But you really don't need, you can just work with these locally diametrical. And that saves you a lot of computation. Okay, so I'll show you what that is. So let's just do a construction because this is kind of fun. The fun part of hyperbolic graphs is doing these estimates. So let's see if we can calculate the R1, the one packing of a graph. I want to find a single center so that the whole graph is within a ball of minimal radius from that center. Okay? So I do what I just told you. I find the locally diametrical pair x and y. That's order n. Then I take the center of it, C. And I want to claim that C, a disk around C with radius, the smallest circle that will contain the whole graph, is bounded from above by the optimal radius plus delta. If I do something, I have no idea what delta is, I have no idea what the optimum distance is. Find a pair of points that are diametrically opposite, locally diametrically opposite. I take the middle, and then I do a breadth-first search until I find the furthest point. And I claim that that distance is already within delta of the object. Okay, so let's see how the construction goes. Since xy was locally diametrical, that means any point z, the distance from z to x is less than or equal to xy, and the distance from z to y is less than or equal to xy, by construction. We couldn't find the point z that was further away from either x or y. Okay. So distance between y and z is less than xy, and z and x is less than xy. Remember that useful property I mentioned? If you're looking at the larger side, your internal distance is smaller. So by definition, this means that alpha z is less than alpha y, less than alpha x. Alpha x looks like the smallest side, so it's the larger. Now find the path from z to this center, or an approximate path. So the path is, I'm not going to go directly because I have no idea how to bound it. I'm going to go zigzag. I'll go from z to mx, then from mx to mz, from mz to c. Z to mx is alpha sub c, is that internal distance. By the fact that the graph has hyperbolic constant delta, the distance between mx and mz is less than or equal to delta. And what's the distance from mz to c? Well, remember mz to c is c to y minus y to m. C to y was half the length of the side xy, and y to mz was alpha sub y. So the estimate of the distance from z to c is alpha z plus delta plus lambda minus alpha y. And we know that alpha y is bigger than alpha z, so that means this difference is negative, so it's bounded by lambda plus delta. So it's a medial construction without any knowledge of it. Because if we know what delta was, that would be a lot of work. We don't know what it is, and yet it works. It gives us the necessary bound. Often lambda is less than the diameter, half the diameter. So this bound is actually lambda plus delta, not r sub 1 plus delta. Lambda is less than r sub 1. So that gives you a flavor of how things work out. You basically, working in this geometry, you constantly estimate distances by using these, the fact that triangles are delta thin. You have to break up the space into a bunch of triangles, and then you patch these distances up and use the hyperbolic constant to bound. Okay? So, okay. So, p-centers of a graph. Remember that result that Shire used. Shire said that if you take a geodesic path that is maximal length, and if you go into it a distance lambda, and if you draw a disk of radius lambda around that center, it includes the disk of radius 2 lambda from the end. We can now prove the same thing with a slight error in a delta hyperbolic space or graph. Basically, we can prove that the ball around y of radius 2 lambda is included in the ball around c of radius, before it was lambda, now we add the hyperbolic constant. So it's a little bit larger. This is a slightly larger disk. And again, the proof is the same trick. You assume either, you take z, you start with the locally diametrical pair, which you can compute in order n. Then you look at any point z, that has to be, the distance from z to y has to be less than 2 lambda by construction. And then you decide, then you go on this geodesic distance lambda from y, and you call it c. In this case, you have to consider two possibilities. Either c is to the right of the internal point or to its left. Here you see to the right is exactly the same argument that we just saw. And if it is to its left, you get another argument. You get, in the estimate, you get alpha sub z plus alpha sub y. Alpha sub z plus alpha sub y is this sign, which is less than or equal to 2 lambda. So we have delta minus lambda plus 2 lambda. That gives us again the lambda plus delta. So this is the key observation, is that we can actually replicate Shire's original observation and why his scheme worked using locally diametrical pairs. So now we actually have a recipe for finding the p-centers of a delta hyperbolic graph with hyperbolic constant delta. So what do? We do exactly the same thing as before. We find the pair of diametrically far pairs of nodes. Then on each side we take it. We are doing it for a given lambda length. We want balls of radius lambda. And then we go on the shortest path, the distance lambda, and we call it a center. And then you remove a disk. This time of radius lambda plus delta. So we repeat this and we have a construction.
So your notation, sorry, third bullet we say, on geodesic xy, I find the center C, and that means I call distance lambda from x.
That's correct. The notation is square parenthesis means geodesic, the shortest path. And then you put a length after it. That's how far you go into that geodesic. So again, the reasons why it all works is because of this packing and covering duality. Because every time I create a disk, I know that the points outside that disk are going to give me a packing. Right? So that guarantees that we have optimality. In this case, we have a proof. The packing is smaller than covering. But packing is bigger than covering of disks with slightly larger radius. Okay, so this actually gives us an order n squared approximation for the epicenter. The prior work of Chapoy and so on had an order n cubed. So through this locally diametrical pair, we brought it down by 1n. But still, if you want to calculate epicenters for graphs of, say, 10 million or 100 million, not going to work n squared. So we have to work harder. Here we still have the same approximation as before, delta. An error of delta is all paid. And again, since delta is small, this is not a big, huge cost. Okay, so the question is how much time? What I can tell you is that this should be on archive next week, so you can read the details of the proof. But I'll give you the construction. So how does the construction work?
So to remember, you go down from n squared to what?
N cubed to n squared.
But okay, you go lower.
Yeah, we want to go to n.
To n. And you did it.
Yeah, and the problem is now we are going to have to give up the delta approximation and suffer. Right now we can't see how we can bring it below 3 delta. So we can do it. If it is one center, I showed you one center with 1 delta, and 2 center works exactly the
So
same.
you're going to do a less tight approximation than the other.
Yes.
You're going to go 3 delta versus
Yes.
okay.
And for we can see how we get the linear algorithm if we do 3 delta. I'll tell you the construction. The construction uses a slightly different notion of packing. And this was also has been used by others extensively. So before I said the packing has to be such that an R packing, the distance between a pair of points has to be strictly greater than 2R. So the disks don't touch. Now we allow the disks to touch. That means the packing can be tight and the disks touching. So the pair of points in the packing can be as far as 2R. And you can convince yourself of the following fact. In a tree, so let's take a value P2 just for the sake of argument. For a tree, if you take 2 centers, you want to find 2 disks, you can find 3 points that have the same radius as the covering. If we use this less strict notion of packing. But if we stick to the strict notion, we'll find only 2. So why do we go from P to P plus 1? That follows from pigeonhole principle. So if I define packing to be distance 2R or more, then if I have P plus 1 points in a packing, if they can belong to the same, if I have about P disks that cover the graph, then 2 of them will have to be in the same disk. Therefore, the maximum distance is less than or equal to 2R. So this is a construction that says I allow weaker packing, but I have to go 1 extra point. So if I'm interested in 3 centers, I'm going to look for 4 points that are maximally far from each other. Okay. So this gives us a, so it's not hard to see that the distance, the P plus 1 packing divided by 2 has to be less than the radius. That's the vision of the one. And Shire proved in the 1976 paper that on trees these are the same. Meaning the packing radius divided by distance divided by 2 is the covering radius. Okay, so there is a very nice extension of Shire's result by Chapoy in the 2007 paper. They show that this packing diameter divided by 2 is now less than RP that we had. But that is also bounded by half the diameter with P plus 1 point plus delta. So they give a delta approximation of the same result. And that's really the basis of the n cubed algorithm. Okay, so I'll give you the construction and then I'm going to show you some computational results here. So the way we do this, we want to generalize this notion, this useful concept that we actually used extensively, which is the locally diametrical pair. So we want to extend it to a locally diametrical set. So what is a locally diametrical set? Locally diametrical set is a set of points that are maximally far away from each other. And one way of constructing is you start with a locally diametrical pair, so there's nothing that's further from them than the current distance. Then you add another point that's as far away from these two as you can get, which means the minimum of the distance between the new point Z to either of these is maximized. That we can compute with 2 order n breadth first search computation. Okay, so that gives us the third point. Then we look for the fourth point. We do 3 breadth first search starting from these. So if you look at every point in the graph and say what's the distance from that point to every one of these 3 points, and we want to find the point whose smallest distance is as broad as possible. These are all order n. So we find a set like this, we call this a locally diametrical set of size p plus 1. We want to solve the p-center problem, so we go 1 up because we know that the smallest distance in this package has to be some kind of a bound on the cover. However, when you try to do these approximations using the hyperbolic triangle, then you run into a problem in that the trick with the approximate length doesn't work. You need to tighten the distance between these points. And the tightening is exactly what's described here. So, first of all, you start with a set of p plus 1 points, then you look at a point that's outside that is more than 2 lambda away from some of these, and then you switch it one of the existing vertices with that. So basically, iteratively and in order n, you push the distances that can be increased to the current set, because at each point you have a maximum distance from the current set. But you look at other points and see if you can improve the distance to other points. Okay. So this is kind of a pushing the node to the boundary. And what we are able to show is that if you take you take the pair that has the shortest distance, so that's the bound of the packing. And then you take half of that, that's the radius of the covering disk. And you split the centers away on the geodesic that is at the end of the vertex 0, which is one that has the shortest distance to some
The lambda is now the minimum, the minimum, describe the minimum distance between the sets is that the point is that set.
That's correct. So again, you do this, and lambda plus 3 delta is a bound on the on the disk. These disks are no more than optimal or plus 2 delta. And the fact that lambda is less than r sub t, which is the optimal, this is obvious because lambda is the packing distance for a finite subset of the points of the graph. So it can't be ignored. You're underestimating it. Okay, so to summarize, we have order n cubed is the best that exists with an approximation additive error of delta. We can use tree approximation. That gives a very poor upper bound. So you can show that there is a tree approximation of the delta hyperbolic graph that has an error of 2 delta log n. But if the diameter of these graphs are of order log n, then 2 delta log n is not such a great. Right. So this is not very useful. But it works in practice rather well. And then in our case, we have an error of delta or 3 delta when p is greater than. When we're looking for more than 3 points. So here's one example. We took the archive repository of all the documents written in the past 10, 15 years by the lab's authors, and we constructed this co-authorship graph. So there's about 16,000 names of authors, and there are 76,000 edges. What's an edge? 2 authors are connected if they have written a document together. And as you can see, this is the actual construction of the graph. This is not a carpet. These are little cliques that exist. So this is the largest clique, and that's what we're going to be working with. But mysteriously, there's a whole bunch of people that have written documents together, but with nobody else.
And they're completely disconnected from the rest.
Completely disconnected. Now, I have to say, when we looked at some of the data, when the secretary was entering the name of an author, the author was John Barras, and his BA control F-A-R-S. So the name appears with a control character in it. So that's different from you. So that we haven't been able to completely remove all these. So I suspect a fair number of these cliques are actually names that are misspelled or they have control characters. The actual text processing in these things can be exhausting. At some point I decided to remove these control characters by just eyeballing them. And after I went through 2,000 records, my eye muscles were completely frozen. And I decided it wasn't point, and there was no more point in going further. But it's hard to catch these. Any other way than just look, when you look at them, you see, oh, there's a control character, there's a caret mark to remove them. But you write scripts to remove them. It's not clear what you should be looking for. So anyway, so that explains some of these. Delta is about 3 or 4, I forget. And here is the tree approximation on the left. Here is our 3 delta approximation of the graph. And as you can see, the tree didn't look too badly. The tree has a very poor upper bound. It's 2 delta log n, which is useless. But in practice, we never hit the upper bound. By the same token, we hardly ever hit our upper bound, which is 3 delta. This 3 delta can be large. If delta is 3 delta is 9 halves. So that's a significant amount. But we don't reach that, as you can see, plus the radius is 7, which is by itself 1 unit away from our approximation error. So obviously the reality is much better than, but that's not unreasonable because we remember for the distance between the point and the center, we took the zigzag distance and we bounded the zigzag, so it's not surprising that we have a generous upper bound. So what is the ground truth? How do I know this gave us a good cluster? That's usually the hardest part when you use clustering in real life. You have some data, you come up with an algorithm, and it tells you these are the clusters. But how do you know they're good? So in order to, that's the ground truth. So for the ground truth, we did the following. We said, let's construct the word cloud of all the documents that end up in a cluster. So if there's a bunch of authors in a cluster, they have written documents, we pulled all the documents in, we took the title of the document, we created a word cloud. So each cluster is now represented by a word cloud. We had selected 13 clusters, roughly because I decided the work that Bell Labs has done in the past 15 years fall into generally 13 categories. This was a number pulled from thin air. I could have taken 12 or 14.
Can you use keywords to define that, or to define the
cloud?
14 or 15 categories of data?
Oh no, that was just intuition as to what
How do you
area.
define it?
Well, I decided that the work that we don't work on agriculture, we don't work on genetics, we don't work on aircraft engineering.
You use domain definitions
Yes.
or keywords?
No, domain definition. We have people who work in optical networking, wireless networking, wireline networking. We have people who work on algorithms, like we're hearing now. We have people who work on physics, transistors, and solid state. So when I counted those categories, I came up with the number 13. So I said, let's do 13. So the word cloud actually does capture mostly, these are the top 6. You know? The other 7 are not so clean. An author could work, so we found a lot of people who worked on optics and also wireless. And there's actually a historical reason for that. Because somewhere about 15 years ago, the budget for optical research went down, the budget for wireless research went up. So a lot of people who had written documents in optics shifted their expertise and they started working in wireless. And that is the explanation that one of our clusters curiously had both optics and wireless. So that's the reason. So you can actually explain this. But overall, it seems that, first of all, the clusters are reasonably balanced. This is one of the biggest problems with center.
So how should I read this slide?
Okay, so take this one. I am showing 6 of the 13 clusters.
Right, so these are the 6 top or something?
You remember I wanted to have 13 clusters?
Right.
So I'm now showing you the top 6.
Top means what?
Top means in terms of how good they are compared to ground truth.
Okay.
The word cloud tells me, if I get words in a cloud that have nothing to do with each other, then I'm seeing a bad cluster. If I see a word that shows optics, algorithms, wireless, networking, OSPF, then it's everything, right? So that means I have a mission.
But these 6 and these 6 are not the same.
No, these are 2 different algorithms.
I understand that your word clouds, the 13 word clouds are the same.
No. This algorithm gives me one clustering, this one gives me
So
another
what is the
clustering.
ground truth?
The ground truth is by looking at the word cloud and deciding which one is better.
Oh, you do fast I word as well.
Yeah. Fast fiber transfer. FE. Yeah, so, I mean, look, this one is organic, quantum, transistors. I mean, it makes sense. And then this one has data, survey, digital, whatever.
But wouldn't it be better if you have keywords that you see?
But the question is, when you start working with this kind of data, you very quickly realize you can't trust anything. You know, so SIGCOMM may have very rigid classification, but as an author of SIGCOMM paper, you know at some point, 24 hours before the deadline, you have to put a classification on your paper, and you eyeball the list that you had, and you just pick the one that fancies you.
And many times I do the paper, you're right.
I mean, obviously, as an author, you do a lot better job, but there's no guarantee.
So So would you say, okay, if you look at these 2 6 now, 6 here, 6 here, right?
Yeah.
Can you make a comparison?
You know, they're both good. As the previous slide also,
Not bad either.
not bad.
So how do you discriminate?
But in this case, I actually concluded they're both reasonably good. And the one on the left is a lot faster.
Okay.
This was, we were trying to benchmark, and the benchmark was show that it was okay. So I'll show you another slide which is impressive. This is the call graph. It's about 50 million nodes and 300 million edges. Right? So we could solve the p-center about 10 seconds for each p.
That's, where here, a link means these people call each other sometimes.
Yes. They have to at least talk to each other a few seconds before they, because that could be a mistype.
I think we're looking at this. Can you do polarity analysis on this graph to figure out who called first whom and then who called after that and so on?
Yeah, because the log files include that.
The log file is directly, right?
Yeah, the log files have all the information. The problem with these data, we had this data for about a month, and then that's all we had. It was anonymized, and we had access to it for only 1 month. So we were not only trying to speed up the computation to see the performance, we were also trying to speed up computation because the data would vaporize. Nobody trusts anyone with these data anymore. So it's very hard to get this kind of data. But if you get a hold of these, you have all the information. So this is the curious thing. With 12.5 million centers, every node in the graph, which is 15 million nodes, 4 times as many, is covered in the radius 1. So, and just looking at the statistics of this gives you a lot of information. That's why the meta information is so useful. And that's why initially everybody thought, no, it's not a privacy violation, we're just looking at meta information. And then you look at the meta information and it actually provides an awful lot of analysis and summary of it. Okay, I think I've exceeded my time by a few minutes.
Okay. Very good. Thank you very much.